Hello everyone, here are the solutions to logs day 8. I'll slowly scroll through. Let me know if you have any questions on these. All right, here are the answers to the even problems from section 2.3, the textbook exercises. Now I'm going to take a look at a couple of the odd problems that I have in mind. But let me know, even on 11 through 18, they were just, they gave you this piecewise function along with the graph and then just asked you different questions for each type of problem. So again, let me know if you have any questions over these. If you do, I could create another Zoom meeting. I know we usually do ours on Tuesdays, but if I get quite a bit of questions from you guys, let me know and I can set up another Zoom meeting, probably for maybe even on Friday. Just let me know. All right, so I want to take a look at 29. Here we were, it says give a formula for the extended function that is continuous at the indicated point. So we know if x were to equal 4, we would get a 0 in our denominator here. So we could still, it's not common to see problems like this, but we could still simplify this by factoring. Even though the numerator isn't your typical difference of squares, it can factor. And if you use the denominator as a clue, we could factor x into radical x times radical x, and then the 4 can be a positive 2 times a negative 2. This way we can divide out the radical x minus 2's, and then we're just left with radical x plus 2. So we could start or state a piecewise function here. That now when x is 4, if we're looking at this function, we can say f of 4 now becomes the square root of 4 plus 2, which is 4. So we could create a piecewise function here. And again, we can include the original one. And we can say when x is not equal to 4. And then extend this down here. We could just use the radical x plus 2 when x is 4, or we could just say it's 4 when x is 4. So that's one way to extend it, or again, you can just put that in place of the 4 as well. Now for 31, I'm going to give everyone in class some time to continue to work on this, but it says work in groups of 2 or 3. Verify that the function is continuous and state its domain. Indicate which theorems you're using and which functions you're assuming to be continuous. So this is like going back to some previous pages here, that theorem 7. That was on page 78. So theorem 7 on page 78. So what we could do, and again, pause the video just to look back at that theorem and see if you can decompose this function. And if we could do this, write this as a composition of functions, we could look at each function on its own to see where it's continuous. So I'm just going to, let's just call this f of x is equal to 1 over square root of x plus 2. And all we could do is try and see which ones will make it a little bit easier. So I'm going to write that f of x is just a composition of two functions, h of g of x. So I'm going to let h of x kind of represent the outside stuff. And we have a couple ways to go here. We want to try to do this the easiest way possible. So if I were to let h equal, let's say 1 over radical x, and then g of x, let me write this as h of x, and then let's say g of x would be x plus 2. We could, in a way, work it out this way, but something else that we might be able to do, too, is just say, let's let h of x just be 1 over x, and then g of x could equal the square root of x plus 2. So either way would not be too bad. I think the second way might be a little bit easier to try to determine the continuity. So we could look here and say the domain here is going to be all x's greater than or equal to negative 2. But over here, we can't let the denominator be 0. So this will be 0 if we let it equal to -2. So in our case, we just want to say let x be greater than -2. So g of x is continuous for all x's greater than -2. So I know if I were to do that, my input, these are the input values. The output, so all g of x values here, are going to be greater than 0. And then that's what's going to go here. So that's fine. So g of x is continuous on x is greater than or negative, or just greater than -2. Then all of our y values are going to be greater than 0. If I substituted a -2 or something greater than -2, I'm going to get an output of values greater than 0. And that's great because that's now what I'm incorporating into h of x. So h of x is going to be continuous on all values greater than 0 as well. Again, I can't go less than what would give me, I could go negative over here, but again, I'm not going to get any negative values as my output for g of x. So because h of x is continuous on the interval of all x values greater than 0, I could say that h of g of x would also be the same. So here we could say, therefore, f of x is continuous. So we could look at, and again, the theorem was saying if g of x is continuous at x equals a certain number, in this case x is greater than -2, and then h of x is continuous for all g of x values at that point, and that's what this is saying, because this is all g of x values that we're looking at here. So I'll kind of put it in that way as well. So g of x is continuous on x is greater than -2, and h of x is continuous on all g of x values greater than 0. Therefore, f of x is continuous on x is greater than -2. So that's what just using that theorem is kind of looking at here. Now, granted, we could just go back up to this and determine the domain and say that it's continuous everywhere on that domain, which turns out to be all x values greater than -2 as well. 33 is the same. I'm going to leave this one be for right now, and then if you guys have more questions, but just because I modeled number 31 there, you can try 33, and then let me know if you have questions. All right, so looking at the next section here, section 2, we now start to take a look at rates of change and how they apply to tangent lines. So before, we were looking at what we can consider the average rate of change. And we'll still start with this right now, but we do this in algebra. For example, if we're going 120 miles in 2 hours, then we look at the change in distance over the change in time. So this would become delta D. So the change in distance over the change in time, which would just give us 120 miles in 2 hours, or 60 miles per hour. So that's everything that we were doing, especially for slope. Change in y's over change in x's was the average rate of change. But now, if we were to look at something called the instantaneous rate of change, that's what we use calculus for, and to get us to that point, we use limits. That's what separates algebra from calculus, is this idea of limits. All right, so first we're going to graph this function, this quadratic function, just over the interval from 1 to 3. So definitely when you go to number your coordinate plane, spread it out a little bit. And definitely number high enough up on the y-axis here. Okay, so if we have something numbered like this, and again, I just substituted the 3 in to see how high up I needed to count here. Because again, we're just going from the interval from 1 to 3. We might draw the graph a little bit more to the left than necessary, but let's determine the vertex here. So you could complete the square, but let's go back to that technique I showed you guys at the very beginning of the school year, where h is equal to the opposite of b over 2a. So that's going to give me a negative 2 over 2 times 1. So I'm just going to get a negative 1. And then k, because our vertex is hk, k is just going to equal f of h, which is f of negative 1. So that's just going to give me a 1 minus a 2 minus a 1. So we're going to get a 1 minus 3, so it's going to give us a negative 2. So our vertex here is at negative 1, negative 2. Put the negative 2 down here. All right, so again, if I go over 1, I'm going to go up 1. Over 2, we'll go up 4. I want to put it there at the origin. All right, so we should have something that looks like this. So I have a point right here at 2, 7, at 3, 14, and then at 1, 2. All right, so if we're asked to find the average rate of change, that means we just want to draw a line that's passing through these 2 points that starts at 1 when x is 1 to x is 3. And we would call this a secant line. Any line that crosses through a curve at exactly 2 points is going to be a secant line. And the average rate of change will just then be the slope of the secant line. So I'm going to write it this way, slope of the secant line. So in this case, it's going to just be f of 3 minus f of 1 over 3 minus 1. That's nothing more than the y2 minus y1 over x2 minus x1. So we're calculating this. This will give me 14 minus 2 over 2. So this will give me the slope of my secant line is going to be 6. So therefore, the average rate of change over the interval of 1 to 3 of f of x here is just going to be 6. So let's generalize this average rate of change. All right, so let's say I just have some curve looking like this. I'm just going to call this f of x. I'm going to pick 2 points here. I'm just going to call this first one x. And then so many units to the right here will become just x plus h. So I'm going to put 2 points on here. So now this would be the ordered pair x comma f of x. And then this would be the ordered pair x plus h comma f of x plus h. Now if I wanted to find the average rate of change, again, I would draw a line. It's going to be a secant line going through these points. I'm going to change that color there. All right, so again, this is our secant line. All right, so again, the average rate of change is equal to the slope of the secant line. And based off of the generic points I picked here, this is going to be our y2 minus y1 is going to be f of x plus h minus f of x all over x2 minus x1, so x plus h minus x. Well, then by cleaning up that denominator, I still get f of x plus h minus f of x all over h, because the x's cancel out. So this is the generalization for the average rate of change, the slope of the secant line. Now what I have here, these next couple slides, it wasn't a separate Inspire doc. I'm just going to kind of go over these with you. Here we're looking just at the graph y equals x squared. So the tangent line to f of x at x equals 1 and a secant line are drawn in. So the tangent line is what's in green, the secant line is here what's in red. So if I were to grab and move this, so notice here my change in x's are just 2. I'm going from 1 to 3. Notice the slope of the secant line here is 4, slope of the tangent line is 2. In the next slide, I'm changing that distance. I'm decreasing the distance. My delta x is going down. So now the distance between my two x values is 1.25. Notice how the slope of the secant line looks a little different. It's less steep. That's here. So the slope of my secant line is a 3.25. Slope of my tangent line, I still had the calculator do this, is 2. Let's do this a couple more times. Now my x values are even closer together. My delta x is a 0.432. Notice how the red line, the secant line, is now changing. It's getting closer to approaching the green line. So here the slope of my secant line is 2.43. Slope of my tangent line is still 2. Let's decrease delta x a little bit more. Now it's a 0.153. Notice how those 2 points of my secant line where they intersect are very close together. So my red line is getting even closer to where that green line is. Slope of the secant line is 2.15. Slope of the tangent line is 2. Therefore, we could say the slope of the tangent line of a function at any point is if we just put this limit as delta x is getting smaller and smaller. So here, rather than using x and h, they used x and delta x. But this would still be the same as h approaches 0. So just to show this here, the slope of the tangent line is the function for the average rate of change, but as we take the limit as h approaches 0. So we could say as h approaches 0, the slope of the secant line is going to approach the slope of the tangent line. So as our points are getting closer and closer together, we keep one point fixed, and that's the point of tangency. As that other point keeps moving closer and closer, meaning the distance h between the two x values is becoming practically 0, the slope of the secant line is going to become the slope of the tangent line. Okay, so let's take a look at an example here. We're going to find the slope of the tangent to y equals x squared at a specific point x equals 2. So I'm going to start, the slope of the tangent line is equal to the limit as h approaches 0 of this function that we just wrote out. So we're going to find this generally at first, and then we'll substitute in the 2 that's there. All right, so if our function is x squared, we're going to have x plus h squared minus x squared. So this is f of x plus h, and then just minus f of x, so that's going to be x squared all over h. I'm going to expand this. So this becomes x squared plus 2xh plus h squared minus x squared all over h. Still can't substitute in 0 for h just yet. If you notice in my numerator, the x squares cancel out. So I'm just going to get 2xh plus h squared all over h. Now what I can do is every term has an h, so I could divide throughout by h. So now I get the limit as h approaches 0 of 2x plus h. Now I could substitute in the 0 for h, so this will just become a 0. And now I just get 2x. So this is the slope of our tangent line. Now at x equals 2, the slope of our tangent line becomes 2 times 2, which is 4. So the slope of our tangent line is 4, specifically at this x value of 2. All right, so hopefully I could get through this whole lesson in class. I'll let you guys know tomorrow. So if I don't do this in class, then this assignment right here will be continued tomorrow, but you can go ahead and work on it now and actually become a day ahead if that's the case. But go ahead and definitely work on logs day 9 and 10. And then here, given f of x is equal to x squared minus 4x at x equals 1 here, find the equation of the line tangent to f of x at x equals 1. B is a little different. Find the equation of a normal line. A normal line is just a line perpendicular to the tangent line where it is tangent to the curve. And then check your answers to A and B by graphing on your Inspire. Make sure you still go back over pages 80 and 81. Let me know if you have any questions. Into next week, we will be looking at the Chapter 2 test. More information will come on that for the rest of the week. All right, guys, take care and let me know if you have any questions.